Rosen, Discrete Mathematics and its Applications, Section 4.3 on primes and greatest common divisors. In this section, we'll learn about prime numbers and probably most importantly, the Euclidean algorithm. A prime number is a positive integer p greater than 1, and its prime if its only positive factors are p and 1. Any number that is not prime is called composite. The integer 7 is prime because it has no factors other than itself and 1, but 9 is composite because it has 3 as a factor. The fundamental theorem of arithmetic is that every positive integer greater than 1 can be written uniquely as a prime or the product of two or more primes where the primes are written in non-decreasing size. For example, 100 can be written as 2 squared plus 5 squared. 999 is 3 cubed plus, or times 37. I think I said plus earlier. It's times. 1024 is 2 to the 10th, as many know. And 641 can be written as itself since it is a prime number. This is the famous sieve of Eratosthenes, where we can use trial division to determine all the prime numbers less than a certain value. We're going to look for all the primes between 1 and 100. So what we do is we start dividing or looking for those that are divisible by the lowest primes. The first prime is 2, so we delete all of the integers other than 2 that are divisible by 2. Since 2 is prime, we leave it. Delete all integers other than 3 that are divisible by 3. Delete all the integers other than 5 that's divisible by 5. In other words, we're getting rid of all the composite numbers between 1 and 100. And then one more we'll look at. Delete all integers other than 7 that are divisible by 7. And then the remainder will be the prime numbers if we don't count the 1, which is not considered prime nor composite. And here they are. And there's 25 primes less than 100. Your book will have a figure that looks like this that illustrates going through all of those deletions, that leaving the prime numbers. And it turns out that we only need to consider the division of numbers less than the square root of the largest number that we're looking at. And the reason for that is if it is a composite, it's going to be equal to a times b, and one of those two numbers will be less than or equal to the square root of n, allowing us to capture the other number. What we've done is an instance of trial division. It's a way of determining prime factors of a number by dividing by lower primes in order to get all of the factorization of a number in terms of primes. But it is very inefficient way of going about determining whether a number is prime. One more topic. There are an infinite number of primes, and this was given by a very famous proof by Euclid. And we're going to prove that there are an infinite number of primes. We're going to do it by contradiction. So we'll assume that there are a finite number of primes, p1 through pn. And we're going to form Q, which is the product of p1 through pn, and we'll add 1 to it. All right, so now what can we say about Q? It's either prime, or by the fundamental theorem of arithmetic, it is a product of primes. Well, if it's prime, we're already done because it's not going to be on our list. But look at the form of my sum here. None of the primes pj can divide q, because if it divides q and it also divides the product of all the primes, then it must divide 1, and 1 cannot be divisible by a prime number. This is the result of a theorem from the first section. So either if q is composite, then it must have a prime factor that's not on the list, or it prime itself, in which case, either case, we violate the contradictory assumption, so we conclude that there are an infinite number of primes. And again, this is considered one of the more famous and even beautiful proofs, and was mentioned by Paul Eratosthenes in his book called The Book. And that's your introduction to primes.